Today I'm going to talk about quantitative analysis of copper electroplating on zinc strip. The extract of this experiment is the experiment aims to perform the electroplating of copper onto a zinc strip using copper 2 nitrate solution as the electrolyte. This is to validate the Faraday's first law of electrolysis by measuring the mass of copper deposited on the zinc cathode over time. So we move on to the introduction. Electroplating is one of the most commonly used techniques in material science and industry. This involves the electrodeposition of a metal onto a conductive surface via an electrolytic process. The governing principle is Faraday's first law of electrolysis, which relates the amount of materials deposited to the electrical charge passed through the system. So, the materials and procedure that are used in this experiment is for the materials we have a DC power supply, a beaker 250 milliliter, zinc metal strips and copper metal strips, connecting wires with crocodile clips, ammeter, digital balance, copper 2 nitrate solution 0.5 molar, and distilled water. So for the procedure, 0.5 molar copper 2 nitrate solution was prepared. The apparatus was set up as the picture, and the experiment was run with 2 to 10 minutes. After each interval, the zinc strip was removed and weighed at the mass and weigh. All the masses was recorded for each experiment.
In this experiment, we aim to validate Faraday's first law of electrolysis by observing how much copper deposits onto a zinc strip over time. According to the law, the mass of a substance deposited in an electrode is directly proportional to the electric charge passed through the electrolyte. This relationship is defined by the equation M equals to IT M over NF, where current and time determines how much copper is deposited. Although our procedure initially called for a constant current of 2.0 ampere, we had to adjust this to a 0.2 ampere because our power supply couldn't deliver a stable current at that level. Despite this limitation, the trend we observed still supported the theoretical expectation. As time increased, the mass of copper onto the zinc strip increased steadily from 0.04 grams at 2 minutes to 0.29 grams at 10 minutes. This confirmed that even at a lower current, the relationship between charge and mass still holds true. There were some minor irregularities in the rate of deposition, especially between 6 and 8 minutes. This could have been caused by small fluctuations in current, possible uneven copper build-up on the cathode surface, or slight errors when drying and weighing the zinc strips. In some cases, retained water or accidental damage to the copper layer could have affected the mass measurements. To reduce these sources of error, several precautions were taken. We ensured the electrodes were fully dried before weighing, and we handled the zinc strips carefully to avoid dislodging any deposited copper. For more accurate results, using a more stable power source and gently stirring the electrolyte will help maintain a uniform distribution of copper ions. In conclusion, even with some practical limits, our experimental results align well with Faraday's first law, demonstrating a clear and measurable relationship between time, current, and the mass of copper deposited.
Okay, as shown in the graph, the mass of the copper deposited on the zinc string increases steadily over the time. This trend demonstrates a direct relationship between the time and the amount of the copper deposited, consistent with what we expected from the Faraday laws of the electrolytes. In conclusion, the experiment successfully confirmed the Faraday laws. The data show that the time increased under a constant current. More copper was deposited. Despite there are some minor variations due to the current fluctuation and measurement error, the result closely matched theoretical prediction, validating the relationship between the electric charge and metal deposition.